do Unit 7B, rotational motion, the energy aspects again. The first time I didn't record. Whatever. I was looking at the course exam description book for Unit 7. Specifically, what were some of the enduring understandings, learning objectives, etc. with the energy aspects of rotational motion, and I didn't see any. It talked about torque, it talked a lot about angular momentum. But then I looked at some of the sample exercises or practice exercises, practice activities, and it had several that dealt with rotational energy. And so I'm a little unsure as to what the full expectation is. I cover it very qualitatively, just talking about rotational kinetic energy. And even though, just in case, I think that's an important aspect of rotational motion they need to be familiar with. So the bottom line is, if it's rotating, it's a type of motion. It's a type of moving, which means it has a moving energy. It has a kinetic energy associated with it. I'm going to call it rotational kinetic energy. A lot of people call it that. And so how that kinetic energy is calculated, I don't care that much about in this course. What I care about is, where did it come from? It had to come from somewhere. And not only did it have to come from somewhere, if I'm putting energy into rotational motion, something is getting less energy. And so that's one thing that I spend time looking at and talking about. That's really the bulk of it. If it's rolling, then we have linear or translational kinetic energy. We also have rotational kinetic energy. Now technically the rotational kinetic energy is called rolling kinetic energy. I'm just going to call it rotational because we don't get into all the calculations between rotational kinetic and rolling kinetic. I don't care about them in here. That's what I got. I'm going to look at two common scenarios that I think that there can be expected to see. One of them is comparing the rolling kinetic energy, the rotational kinetic energy of two similar but different shaped items. The other is looking at the same object under different circumstances. First situation I'm going to look at is I'm going to say classic, typical classroom demonstration. We have a disc or a cylinder, however you want to call it. We have a hoop or a ring, however you want to call it. We're going to roll them down a ramp. And we're going to see which one gets to the bottom first. Which one is moving the fastest at the bottom. They're the same radius. Dropped it on my laptop. They're the same mass. Fortunately, not that much. And so here's what I meant by they're similar, but yet they are different. Same radius, same mass. Rolling them down the ramp. I've got a disc and hoop. Disc and hoop. Rolling down ramp. Who wins? Who gets to the bottom first? Which one's going the fastest? This is a very good, along with the next example that I'm going to look at, a very good scenario for a paragraph length response type question. Since they're the same mass at the beginning, they have the same gravitational potential energy. And this is a conservation of mechanical energy problem. And so because it is a conservation of mechanical energy problem, I set it up my conservation of mechanical energy expression. And so At the beginning, they have the same mass, they have the same gravitational potential. They're both at rest. No initial kinetic. At the bottom, they both have no gravitational potential. They both have some kinetic energy. Now the thing is though, this gravitational potential is going to get converted into kinetic energy. It gets converted into translational kinetic, and it gets converted into rotational kinetic. The one that's moving fastest has the higher kinetic energy. Highest regular kinetic energy means higher velocity, because they're the same mass. And so when I look at this, we're gonna argue it through, and I'm gonna compare my cylinder with the hoop. And when I compare the cylinder, and I'm just gonna say, okay, compared to the hoop, my cylinder is gonna be easier to turn. It's easier to turn because I have more mass near the center. Here with my hoop, my turning point's in the middle, all my mass is on the outside. It's farther away. Rotational effect. So because I have more mass near my turning point, this is going to be easier to turn. If it's easier to turn, it takes less energy to turn. If it takes less energy to turn, its rotational kinetic will be less, which means the normal, or I shouldn't say normal, the linear kinetic will be more, which means the cylinder is going to win. This is a good demonstration. It's good to talk about it and have them try to come up with who's going to win, and then you simply do it. I'm sure no real surprise there. I don't get into any of the calculations. It's all qualitative. So the next example in talking about rotational kinetic energy is we're looking at the same object but under different circumstances. This scenario, you can open it up to a lot of variations. Again, very good paragraph length response type question. So let's say we have a ramp and we have a wheel on our ramp, and we roll it down the ramp across a flat surface to the finish line. That's what we got. And we're going to do it under 3 different conditions. Condition 1 is that it rolls without slipping everywhere. It rolls down the ramp across the horizontal surface without slipping. Very nice. In case 2, it rolls, but there's some slipping. So it's a combination of rolling and slipping. And in case 3, it's frictionless. Everything is frictionless. And the question is, rank them. Rank the kinetic energies at the end. Rank the rotational kinetic energy. Rank the translational kinetic energy. Rank the overall energy at the end. And this is a real good question to give them. You can also put a variation is it rolls down the ramp, and then you put these conditions only on the horizontal surface and see how that changes things. A lot of different ways you can address this scenario. But let's look at this. And here's something to recognize. If it's frictionless, it won't roll. It'll just slide, but it slides with no friction. You need friction to have something to roll. The friction just provides that turning force. And so if we're frictionless, it's not going to roll. So this, in terms of kinetic energy, is going to have the lowest rotational kinetic. Lowest rotational kinetic. If it rolls without slipping, this is going to have the highest rotational kinetic because it's rolling the entire time. Some rolling, some slipping, it's going to be in between. I say the lowest kinetic. The lowest, this is actually 0. It's not going to rotate at all. It'll have no rotational kinetic energy. It's going to be rolling the entire time. The highest rotational, that's in between. So if we wanted to rank the rotational kinetic, I've got situation 1 greater than situation 2, which is greater than situation 3. Now the linear kinetic, we have to think about which one is moving the fastest. The one that's moving the fastest is the one that has all linear kinetic energy, which is case 3. It has no rotational, it has all linear, it's going to be moving the fastest. The one that's moving the next fastest is going to be case 1 because it has some. Here's the thing with case 2. We have friction. We're going to lose energy. And so because we're going to lose energy, we're going to lose some of that speed. And so case 2 is going to be the lowest. Case 1 is going to fit right in between. The total energy at the end, case 1 and case 3 are going to be exactly the same because mechanical energy is going to be conserved. Yeah, we got some rotational, but the rotational plus its kinetic is going to balance out with our all kinetic there. And so when we're looking at the total energy, case 1 and case 3 are the same, but because we lose some energy with some of that friction, case 2 is going to be the least amount. Nice little comparison question. Good variation. It rolls without slipping. It's frictionless. What's going to happen to the wheel? If this is frictionless, but it rolls without slipping down the incline. A lot of different good analogies, or a lot of good scenarios that you can come up with there. So this is what I talk about in my energy aspects of rotational motion, Unit 7B. I hope it was of some help. Good luck.